Today we are going to go and look into normal stresses under combined loading. Okay, so I'm going to teach you a procedure on how to analyze stresses in 2D and also in 3D later on. Okay, so I have posted these diagrams on Avenue to Learn. If you can go to Avenue to Learn to fetch them, it will be fantastic. Okay, so let's look at this example over here. If we're going to do the first example. Okay, before we do any example, right, or start any example, what we're trying to achieve is this. Okay, so normal stresses okay, are determined using the following formula. So I'm going to call this stress in the x direction. This is equal to px over a. Or before I go px over a, it can be plus or minus px over a. It can be also plus or minus my over iyy multiplied by z, plus or minus mz over izz multiplied by y. Okay, so the most important thing about this formula is to identify the px, my, and mz. Okay, if you fail to determine any of this, okay, your stresses in a particular direction can be is impossible to determine. Okay, so let's go by looking at this example over here. Okay, so this is example 1. And I'm going to teach you the procedure on how to analyze a structure like this. Okay, so given to us, you have a force that is 6 kilopounds. It's applied to a machine element AB. Okay, as shown, knowing from the uniform thickness of the element is 0.8 inches. Determine the normal stresses, shearing stress at point A, point B, and point C. Okay. So by looking at, so we have to determine elements A, B, and C, as you can see over here. Okay, this is what we have to determine the stress state. Okay. So the first thing, as you can see, the transformation is not given. Okay. So now we are going to declare that this is our X, this is our Y, and then we have rotation about Z. So to visualize what is our cross-sectional area look like, so I'm now going to sketch a cross-sectional area. And if cross-sectional area, this will be our Y, this will be our Z, okay? And then using right-hand rule, this is rotation about X. And then I'm going to sketch out the cross-sectional area. Okay, so this is how the cross-sectional area look like. And it's given to us the dimension from here to here. Right? This dimension over here is equal to 3 inches. And also given to us, the dimension from here to here is 0.8 inches. Okay, so a very important thing is the transformation. Okay, you have to draw this and make sure you have the right orientation, because if you get it wrong, that's where the snowball effect will happen. Okay, you get it wrong, and then when you determine your second moment of area, that's where you're going to have trouble. Okay, so the first thing that we're going to do is we're going to determine what is our px, what is our my, and what is our mz. Okay, so the first thing we are going to do, we know that over here we can resolve into two different forces. So the first force over here, right? So this is our AX, and then we also have another force over here, and this is our AY. So very quickly, we know that AX is equal to cos 6 times 10 to the power 3. And then we have cos 35. Right? So the outcome of this, 6 power 3 times cos 35, 4.915 times 10 to the power 3 pounds. Okay, and we can also determine our AY. Okay, so by looking at AY, we now have 6 times 10 to the power 3, and then we have sine 35. Okay, so the other one, so it's sine 35 times by 6 power 3 is equal to 3.441 times 10 to the power 3 pounds. Okay, so we know the elements of interest. Okay, is A, B, and C. So the first thing we are going to do, number one, this means procedure number one is sketch the centroid that is relative to the elements of interest. So for this case, A, B, and C. So if we're going to sketch the centroid, it's just a sketch for now. Okay, this is how the sketch will look like. You see the green line? Okay, so this is where this is our centroid. Okay, centroid that is relative to the element. Okay, so there are two ways of doing this. Okay, so the thing that I want to teach you is we are going to identify, okay, what is our px first. Okay, So the thing we have to look at is when the force or when the force or when the component is parallel to the centroid, right, it will generate a axial force. Okay. So if we were to now focus on AX, right, AX is going to generate a force, an axial force over here. Okay. And this is also our AX. Okay. Or I won't call it AX. Down here, we know that this will generate a load that is 4.915 times 10 to the power 3. Okay. So that is what you can see now. Okay. Then another thing that we can say about AX, okay? So we know that AX will generate a moment about Z. Okay, so we are aware that AX, okay, AX will generate a moment about the central or about the Z-axis. Okay, so the moment generated by AX, okay, what is this moment? Okay, so moment about Z. Okay, so I'm going to declare this. Anything that is anti-clockwise, right, is positive. So moment about Z will be equal to what? Okay, so will be equal to AX multiplied by a distance of 8 inches. Okay, AX multiplied by a distance of 8 inches. So AX is equal to what? 4.915 times 10 to the power 3 multiplied by 8. Okay. And we know it's negative because it's going in the opposite direction. Okay, so 4.915 power 3 times 8 is equal to 39320. Okay, it's equal to minus 39320 pound each. Okay, we know that. So now, one thing I want you to observe regarding AX. Okay, when the force is parallel to the centroid, okay, the perpendicular distance okay, the perpendicular distance is to the centroid. Okay, so for this case, AX is parallel to the centroid. The perpendicular distance is 8 inches. Okay, why this is important? Because as I said, I taught this course too many times. Students get confused. Okay, they'll say if it is element A, right, the perpendicular distance is here to here. Yes or no? Right? And then where it's element C, the perpendicular distance is here to here. No, that's not right at all. Okay. Then you ask me, Eugene, why is it to the centroid? Because if we look at the formula, right? If we look at the formula, we know that stress X is equal to plus or minus mz over izz multiplied by the y. This y, right, will compensate, will compensate whether it is element C, element B, or element what? A. Mz, okay, when the force is parallel, okay, parallel to the centroid, the perpendicular distance is what? To the centroid. Very, very important. Okay. Do not get this mixed up. As I mentioned before, a lot of students got this mixed up. Okay, you have to pay attention to this. Okay. Right. Next. So we have done with AX. Now we are going to focus to AY. Okay. So if we were to look at AY now,